How you doing today, Daniel?
Hello, testing, testing.
I
Can you hear me?
Yeah, I
Oh,
can hear you now.
I wasn't turning green. I just woke up, so I'm waiting for my coffee to brew.
Okay.
Um,
Can't think of a better way to wake up than to do some Cal 3.
this is how I've been going all semester. I wake up the moment before class starts.
Yeah.
So I'm ready.
All right. All right. Hello, everyone. It's 1 o'clock. I'm gonna jump right in because we have a lot to do. I'm trying to get through enough material so that you'll be able to do that next mini exam. So last time we were talking about line integrals, and then we got halfway through the section and we converted our idea into line integrals over vector fields. And the main result was this new line integral of a vector field dotted with dr, where dr represents the unit tangent vector of the curve dotted with the, or sorry, multiplied or scaled by the infinitesimal arc length. We went through this already, but just want to remind you, this was the main formula that we're going to be using here. So we're going to get into the next example that I did not get a chance to do last time. So the previous example we did was this one. We were trying to find the work done by the gradient vector field of this scalar function on some path. So next example is we're asked to find the line integral over the vector field f dot dr, right? So using the formula right here, we need to take f, make this a little bit bigger. We need to take f, we need to evaluate it along the curve, okay? So this is the curve C, evaluate f along that curve, dot that with the derivative of the curve function or the vector function of the curve. So we have a few things to resolve here. The big thing is let's figure out what r of t is, which would be the curve itself. So we're told here that C is the parabola y equals 1 plus x squared. Hold on, gotta close this and reopen it. All right, there we go. So y equals 1 plus x squared, and we're going from the point -1, 2. So let's graph this real quick. So here's our parabola, but we're only going to be going from the point -1, 2, which is going to be here -1 to 2. And then we want to go to 1, 2. And so we're going to be moving just along this part of the path here, that's C, and we're going to be moving in that direction. So we need to come up with the vector equation for this. So when we do the vector equation, we can come up with a parametric representation of this first. So some parametric representation like x will be equal to something, y will be equal to something, and make both of these functions of t. But since y is, we've already got the equation solved for y, we just replace x with t and replace y with 1 plus t squared. And now something we haven't done before is we will turn this into a vector function where each of the components are simply just those two parametric equations. So that the x component is just t, and then the y component is this. Is that all clear? Okay, we need restrictions on t now. So t is going to be bounded between where and where. Well, here, if we want to start at -1, right, for x and end at 1, then if x is t, then that's pretty straightforward limits of integration, right? -1 to 1. And we're going to need the derivative, so we'll take the derivative of this thing, just so we have it. 1, 2t. And we're also going to need to take the vector field and evaluate it along this curve. And that was some new notation that we hadn't really dealt with before last class. So I told you that doing that is basically rewriting the vector field, replacing the x with the with the x component of the vector function and the y with the y component of the vector function. So we'll do that. I'm going to go ahead and write that down right here just so we have it. Please feel free to interrupt me if you have any questions. So I'm going to rewrite this vector field. X is going to be for us t over the square root of, okay, x squared would be t squared plus y squared, which would be 1 plus t squared squared. And then we're going to do the same thing for the y. I'm sorry, that's not 1. That's not t. That's 1 plus t squared. That's y on top. And then the denominator will be the same thing as the other denominator. So that's what it means to evaluate the vector field along the curve. So we have all the pieces now. We're just going to put the integral together. And let me remind you, last class, we did this same formula. Okay, we did the same formula, but the vector field we were using, right? We had to calculate it because we were told to use the gradient vector field of a scalar function. So because we weren't given the vector field like right off the bat, we had to calculate it. In this problem, we don't. We have the vector fields given. So we just, boom, we just throw it in there and we're off to the races here. Okay, that's it. So now let's do the integral. So my integral is going to go from -1 to 1. It'll be the f field evaluated along the curve. That's this whole thing. I'm going to cheat here. It's that dotted with the derivative, right? The derivative of the vector function, not the vector field, the vector function. So that's this. Oh, no, I don't want that. I guess I could have written that down in the same amount of time it took me to do that, huh? Okay, dt. Okay, so now we dot. So we have to do a dot product. Dot products always result in a scalar or a scalar function. Not we'll have no vectors after we're done with this. So I multiply that times that. That's just going to give you this initial first one here. And then I'm going to say plus, and now I'm going to do this multiplication here to here. So I'll distribute the 2t through the top there. It'll be 2t plus 2t cubed all over square root of t squared plus 1 plus t squared squared, all of that dt. Now that integral doesn't look very nice, but something tells me things are going to get good here. Let's see. Let's combine. They have the same denominator. So I'm going to put the numerator together. I get 2t cubed plus 3t. Y'all agree? That's what I get when I put the numerator together. Then over, okay, the denominator is the square root of t squared plus 1 plus 2t squared plus t to the 4th. I went ahead and expanded out the 1 plus t squared squared. And I did that because I'm going to collect things together there. And I'm hoping that I have a basic U substitution here. Maybe not, but we'll see. So my denominator is t to the 4th plus 3t squared plus 1 dt. And now this problem was made very special so that it would work, okay? Otherwise we get stuck on the integration step. I believe we can integrate this if we make a basic U substitution, t to the 4th plus 3t squared plus 1, because the derivative of that is 4t cubed plus 6t dt. And I almost have that here, right? It's almost what I have here. If I just scale this by a half, I get exactly 2t cubed plus 3t. dt. Lucky for us, right? This matches with this. And so we could just do a basic U sub from here. So I'm just going to say dot, 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 meaning I'm not going to do the rest. Okay. So I mean, in your mind, what are the hard parts about this? What are y'all seeing as being the challenge here?
Writing it.
What do you mean writing it?
There's a lot to write.
Yeah.
I think it's just a matter of actually being able to look at that, some of the integration, and knowing that it's like not as complicated as it seems.
Yeah. I think that the biggest issue that you're going to run into is that when you're doing a problem, knowing what formula you're using. Like, because if we go back in our notes and we're doing a different problem like this one, right? Like, you need to know that the process for this is something completely different, right? It's a different set of formulas you're using. And so it starts to become very overwhelming in chapter 13 because there are just so many formulas. If you know what formula to use, then I think it's just a matter of like systematically breaking it down, just like I did here, right? Just, okay, figure out what that is, figure out what that is, you know, dot it all up, and, you know, whatever happens with the integral happens with the integral, but you've got to have all this right in order to get to the answer. So in my experience teaching this, you know, the big challenge is recognition of what you're supposed to do. Let's look at another one. I'll give you a moment to read that. All right. So you got this man, 180 pounds, carrying a 20-pound tool bag. So basically you got 200 pounds, right? 200 pounds has to go from the ground, and it has to go up a helical staircase that's wrapped around a 20-foot radius cylindrical silo. Okay, so that means we have, so this is a word problem. This is the first word problem we've had in a long time. Okay, so we have like a cylindrical silo that looks like this, right? And this person's going to start here and start walking around a staircase that wraps around, right? Let's see, how many revolutions? 3? Is that what it was? 3 full revolutions. So 1, 2, takes 3 full revolutions, and now the person will be at the top, right? So we need to figure out how much work is done against gravity in order to move this person from here to here. Now, if you've taken a physics class, there's a short, easy way to get this answer. Okay, but I want us to look at it from the perspective of what we're learning right now, because what we're learning right now can extend past a person on Earth. It can extend to any planet. It can extend to any scenario, even where you might not have gravity, like in outer space or something. So we don't want to fix ourselves on using physics only because, well, yeah, I'm going to shut up. Let's just keep going with this. All right. So we want to know work, right? Oh, you know what? Hold on a second. Let me bring up my notes again. I feel like I may have skipped something here. I did. Yes, I skipped a very important thing. Okay, so we just finished this example, right? We had started with this right here. We said that turns into this, right? Okay. Now, we did this example last class, and then we did this example today. There's another note that I need before the next example. The next note is this. Suppose that F is a vector field. Okay, so like in the previous example, here was F, right? It had 2 components to it. This is saying, suppose F is a vector field, a three-dimensional vector field. So it has some P component, Q component, and R component. Then the line integral of F along C is this. So that work integral becomes the line integral of P dx plus Q dy plus R dz. And notice that this expression right here has no vector fields in it, right? Those are all just scalar line integrals from the previous part of this section. So this is now a new formula that we have. Given a three-dimensional vector field, if you want to do this, you can also do this. Now, if you want, you can do this one, okay? You're free to use the general formula. But in the event that we want to, we can use this new integral to represent the work. Now, I'm not going to prove why that's true. You just have to take that on faith, okay? It would take us about 15 minutes to go through it. We just don't have 15 minutes to go through it. So, all right, so I'm going to use that. I'm going to come back to this example now. And I put this formula up here for us, all right? All right, so first things first. Let's see if we can figure out the path. Okay, this person is moving along a path, right? That path is this curve C. There's some things I didn't label here. How this silo has a radius of 20 feet, is that right? 20 feet, it says radius. And the silo is 90 feet tall. So let's try and figure out if we can draw this thing. Can you draw the blue path? All right. So if we're going to draw the path, it's three-dimensional, right? Because that curve lives in three-dimensional space. If you look at it just from the top, if you were looking from the top straight down, what would you see?
A circle.
You just see circle, right? I think I might have this in the notes. I don't want to give it away. Yeah, Sam, I don't want to give it away, but I think this picture helps. If we look at it from the top, we're drawing just basically a circle 3 times, aren't we? 3 circles, one on top of the other, on top of the other. That's if you're just looking straight down. So like in the XY plane, we've got 3 circles. So how do we draw circles? What do we use to draw circles?
The X component is cosine of T and the Y component is sine of T.
Exactly. Now that will draw us a circle of radius 1, right? We need a circle of radius 20. So we just put 20 cosine T, 20 sine T. So the number in front of the cosine and the sine just give you your radius. Now, if I do this and I restrict T between 0 and 6 pi, that will draw me 3 circles, won't it? I'll go 3 circles. One on top of the other, on top of the other, on top of the other. However, I don't want to draw them right on top of one another. I want to, as I draw them, I want to move up, right? And I want to move up linearly. So this is the hard part of this, well, one of the hard parts of the problem is what is the Z component? I always have students that get this and they just get it. And then, so I'm hoping someone can just get this and then I can ask them to explain how they got it.
Is not just T?
I'm sorry?
Is it not just T?
Okay, let's try that. Let's try that, Terrence. Let's just try that. If it were T, then we would start out at 0, right? And when we would end, how high would we be? 6 pi, right? But we need to be 90. We need to be exactly 90 when we get to the top.
Is it 90 divided by 6 pi?
90 divided by 6 pi. And then times T?
Yeah.
Let's try that. 90 divided by 6 pi times T. So let's think about this. If T is 0, where are you going to start? Well, 0, right? So you're on the ground. Now you're gonna, as t grows, the z component starts to grow, right? Linearly. And when I say linearly, I mean linearly because that's all just a number in front of t, right? So that's it's a linear function of t. But see what happens when t gets to 6 pi. When that's 6 pi, the 6 pi's cancel and you get 90. You see? That works. That works. So that's something where, you know, maybe first time you see it, you're like, oh, okay, I see how that works. If you've not seen that before, then it might be hard for you to come up with that, but that'll work. Okay, it's linear. It starts at 0, ends at 90. That's all we need. Now we're assuming that this staircase is not like, you know, wobbly. So it's not like going up and, you know, it's nice and smooth and continuous up there. All right, questions? We have the vector function, right? We have this vector function. Now we need the field. We need the field. So what's the field? What's our vector field?
Assuming that gravity doesn't dissipate the higher we go up, wouldn't it just be a uniform negative 9.8? Or no, we're in feet, so it's whatever the gravitational constant for feet is.
Yeah, so what's the field is the force of gravity. Would you agree with that? That's the only thing that we are working against here is the force of gravity. So the field should just be the force of gravity, which would be straight down, wouldn't it? So that means the x component would be 0, the y component would be 0, and now the z component, what force are we having to overcome? The gravity straight down, right? The gravity on the man in his bag, which is 200 pounds, isn't it? And remember, when I say remember, you may or may not know this. When you look at somebody's weight in pounds, that is a force, okay? Your weight is a force. So this is 200. 200 is the vector that points straight up that is opposing the gravitational vector that's going straight down. So the only force at play here to overcome gravity is that our field needs to be a constant 200 directed straight up as we move along the curve. Does that make sense, everyone?
Wait, straight up, wouldn't it be straight down?
Well, it depends on how we want to look at the problem. Do we want to say what is the work that the man is doing to overcome gravity, or are we going to say what work is done by the gravitational field on the man? There's two ways you can look at it. It's kind of like if I throw a ball to you, is that ball moving towards you? Do we count towards you as positive, or do we count towards you as negative? Does that make sense? Like when you have, there's two ways you could look at something. If I throw a ball to you, I can say, oh, it's moving away from me. So that's 1 foot away, 2 foot away, 3 feet away. And then for you, you could also look at it as coming towards you as something is shrinking or something is growing. It's relative, I guess, is what I'm saying. So I think no matter how we do this, how you want to look at it, if you want to make that a negative 200, that's fine. But we should all get the same answer. Just positive or negative will be the only difference. Am I answering your question, Daniel?
Yes.
Okay. See, it says how much work is done against gravity, right? Against gravity. If it says how much work is gravity doing, right, then that we would look at it as negative. Okay, now look, we can use this formula. We can use it, okay, but I actually think the other formula would be better. Why do you think I like the other formula, the one from the previous example? Why do you think I like this better than the one I showed you?
Product.
What's that?
Cancel two of them with the dot product.
Yeah, we're gonna have to dot this, right? With the derivative of this. And look at, these are all constants. So, and two of them are 0. So the only thing you're really going to get at the end of the day is the 200 times that, or the derivative of that. So I think I'm going to stick with the other way, the other formula. I'm going to get the derivative of this. The derivative of that is negative 20 sine t, 20 cosine t, and 90 over 6 pi is that. So now we set up the integral, and I'm going to use this formula, integral a to b, f evaluated on the curve r of t, dotted with r prime of t, dt. That's the integral from 0 to 6 pi. Okay, the vector field evaluated along the curve. Well, the vector field is a bunch of constants, so I'm not going to plug anything in because those have no impact on the vector field. I'm going to dot that with the derivative, which we just put here. Any questions? And that dot product is really nice because everything goes away except for 200 times this, right? So that's 18,000 over 6 pi. Is that right? I can reduce that, but y'all see what's happening here? 0 plus 0 plus 200 times that. And this is just a constant. So when I integrate that with respect to t, let me reduce that. What is that? 3,000 over pi? T evaluated from 0 to 6 pi. So when I plug in 6 pi, I get the pi's cancel and I just get back to 18,000. And then 18,000 minus 0. So I put here as a note that because we're working with feet and pounds in the problem, that work is measured in foot pounds. So this would be foot pounds.
Quick question. I'm sure that the reason is because you already put that it was in foot pounds, but for the force vector, why didn't we use mass times acceleration?
For this?
No,
Sorry.
for the 200, where the 200 is, why wouldn't we use force times acceleration or mass times acceleration?
Because that's what weight is.
Okay.
So a 200-pound man is the force. I mean, that is his mass times the acceleration of gravity.
Mm-hmm.
Right. So if a 200-pound man on Earth goes to the moon, has the same mass, right?
Mm-hmm.
Different acceleration of gravity. So his weight on the moon would be different than the weight on Earth, right? But if you're saying why didn't we use F equals ma?
Yeah,
we did, because that's what his weight is. 200 pounds is equal to his mass times the acceleration of gravity on Earth.
Mm-hmm. Mm-hmm. Okay.
And that's the only reason we could use it. You're going to see in the next problem, I'm actually going to address that question because I'm going to give you an object's mass, not its weight.
Okay.
Okay. Good question. Now, for those of you who have taken physics, would know that this problem could have been done a lot easier, because whenever you move against gravity upward, the total work done has nothing to do with how far what you do left to right. All that matters is the up and down. So in a physics class, all you would do is take the man's weight with his bag, 200, and since it's in pounds, you would multiply it times the total vertical ascent, which is 90, and that would have given you the same answer, which of course would have been much easier to do, but you know, the thing is, this assumes that gravity is being constant, right? That's something I think Daniel said, assuming that gravity is constant. We know in reality that the further away from the center of Earth you get, right, the weaker gravitational attraction gets. So if you really wanted to make this more accurate, you could not, you wouldn't be able to use 200 here. You'd have to use some variable expression.
The answer would be negligibly different at 90 feet.
Yeah, at 90 feet, it wouldn't be nothing. But I'm just saying, if you generalize this to, you know, a person moving from sea level up to, and you know, somewhere in the stratosphere somewhere, that might impact. Also, you know, there's something here that's also lost in this, and that is you have the curvature of the Earth, right? So if you really look at gravity, I'm going to exaggerate here. Here's the center of the Earth. The actual vector is not straight down, right? Like as you move to different spots on this, so like you have this vector is not just straight down. Now, again, on a silo that's only 20-foot radius, yeah, it's basically straight down. But if you're moving, you know, from the northern hemisphere to the southern hemisphere, then that vector is not straight down, is it? I mean, you know what I'm saying? So if we were to make this, and this is the way everything works in physics. You start out with a basic example, like you take out air, right? You drop a rock and you say, oh, how long does it take to hit the ground? Well, let's neglect air first. And then you start to add in the layers to make it more like the real world. This is like a very basic example that we assume a lot of things to make it an easy calculation. And for the most part, this will work for things like this. But if you want to generalize it, then your vector field is going to have to change. It can't be that easy. And so how would we compute the work? Well, we would just have to evaluate that vector field along the curve and then dot the two and hope we can integrate. Okay. All right, let's look at the next example. A 10 kilogram object moves with a position function R of t equals blah, 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 with t being t going from 0 to 1. Find the work done on the object during this time period. Okay, so I need to state something here that's not obvious in the question. This object is not on Earth, okay? This object is just in space. It is not subject to the force of gravity. So you have some object that's moving along a certain path. Hold on, I gotta sneeze. Ooh. Oh my goodness. Okay. I just got back. My daughter took her to the doctor. She's had fever and chills and all sorts of stuff. I was freaking out. She had COVID or something, but she has strep throat. So I'm hoping that I don't have it. Okay. So this object is moving through space, right? So I don't know how much you know about physics or anything like that. I'm not a trained physicist here, but when an object is moving in space, once you give it some motion, it just wants to stay moving, right? Like all objects at rest stay at rest unless acted upon by an outside force. It's Newton, right? All objects in motion tend to stay in motion unless acted upon by an outside force. So if we have a 10 kilogram object and we want to move it along a curve, even in space, that's going to require force because we have to overcome the inertia of the object itself just to move it, right? And every time we move it, it wants to keep moving in a straight line. But if we're going to move it along a curve, we have to change its trajectory every single moment. So we are applying forces all the time to just make it move. Straight lines, that's one thing, but I'm talking about moving it along a certain curve. I have a picture of this curve. Here's the curve in space. Okay, just see have some sort of idea of what it looks like, okay? So this is an object in space. We want to move it along this curve, which means we have to apply some force to it to make that happen. The question is, what would be the work done in order to move it through that curve? Any questions on that? So work is going to be the line integral over C of f dot dr. But we've learned that that's the integral from A to B of f evaluated at r of t, dotted with the derivative of the position function dt. But that's also equal to the line integral over the scalar function p dx plus q dy plus r dz. So these are the three different, well, these are the two different versions that we have. We have not used this one yet. We've really just used this one. So let's see, do we have r of t? Yeah, it's given to us. We're given r of t, we're given the position, like we're good. Like we know r of t. Do we know r prime of t? Sure, we can do that. That's no problem, right? Derivative of that's going to be 4 cosine 4t, chain rule, 8 cosine 8t, 2t. There's our derivative, right? What are we missing?
F.
The field, right? F, the field. Well, the field that we're talking about is the force, right? The force that we have to apply to the object to move it around. And where'd he go? Oh, Adam. Adam brought this up in the previous problem, that force is equal to what?
Mass times acceleration.
Mass times acceleration. So this you have to know from some previous course, Newton, right? Force equals F equals ma. F equals ma. So for us, this force is going to be our field. Our field should be the mass we have times the acceleration, but we have to look at our acceleration as a vector because the force field, right? The force field that we have is a vector function. And so if mass is a constant, then that means the acceleration has to be a vector function. So where the hell are we going to get the acceleration from?
Is it the second derivative of the position function?
That's exactly right. Remember, if we have the position function, the first derivative is the velocity function, and the second derivative is the acceleration function. So we're going to go and do one more derivative. That will represent the acceleration function. And that will be, let me see, negative 16 sine 4t, and then 64, negative 64 sine 8t, and then 2. Tricky. It's a tricky problem because the field isn't given to you. You have to understand that you are given the mass, right? 10 kilograms is a mass. And so if you're given the mass, then you need to find the force, then you need the acceleration. Because again, we're in outer space, the acceleration is not the acceleration of gravity. There is no gravity. The only acceleration we have is the actual acceleration of the particle moving along the path. So that's the acceleration function right there. So here's what my field is. My field is equal to negative 160 sine 4t minus 640 sine 8t 20. Where am I getting this from? Why am I multiply everything by 10, didn't I? Mass times acceleration. Mass was 10 kilograms. I think we're ready, right? Do we have everything? Do we have the field? Yeah. Do we have the vector function? Yeah. Oh, oops, wrong one. Up here. Do we have the derivative? Yep. We've got it all. So we should be able to do this. Now, I'm sorry, hold on. I misstated something. The field evaluated on the evaluated on the curve, that is just our mass times acceleration. Because that's the force acting on, the objects. It's just mass times acceleration. So it's just this field right here. So we should be able to set this up. Integral 0 to 1. And then it's just going to be this vector function. And then dot that with the derivative, which is 4 cosine 4t, 8 cosine 8t, 2t, dt. And this is just going to be ugly, but it's all going to be doable. So when I multiply these two together, let's see what we get. 4, 640, so negative 640 sine 4t cosine 4t. That's those two. Then I'm going to get plus these two multiplied, and that's going to give me a negative, right? So minus 5120 sine 8t cosine 8t. And then the last one should be plus 40t dt. That might look like a bad thing here, but before I integrate, I'm going to make it a little easier. You could just do basic U substitution here, but I'm going to do something a little different. I'm going to take half of that, that's 320. And then basically what I'm doing is I'm rewriting this as negative 320 times 2 sine 4t cosine 4t. And I'm doing that because 2 sine 4t cosine 4t turns into what? It's a double angle formula from pre-cal. Sine 8t. No? Sine of 2 theta equals 2 sine theta cosine theta. It's one of the big formulas from pre-cal. So it basically says that if you have sine of an angle times cosine of an angle times 2, then you can rewrite that as sine of double of that angle. We usually use the formula from left to right, but you can use it from right to left. And that's what I've done here. I've peeled off a 2 and rewritten that this way. And I'm gonna do the same thing here. This will become, let's see, what's half of 5120? 2560. Sine of 16t plus 40t. And now we can integrate this, yes? I'll stop here, dot, dot, dot. I like this only because I don't have to do any substitution, really. It's just a pretty clean antiderivative. Okay, any questions? All right, that wraps up 13.2, I think. Yeah, that's it for 13.2. All right, moving along, 13.3, y'all ready? (13.3) is titled The Fundamental Theorem of Line Integrals. So throughout your mathematical life, you should have come across a few fundamental theorems. There's the fundamental theorem of calculus. Y'all remember hearing about that? Probably heard about it in Cal 1 or 2. Fundamental theorem of calculus. There's also, before that, there's something called the fundamental theorem of algebra. Somehow students get through algebra without ever hearing about that. And most of the reason why you don't is because it has to do with complex numbers. So you don't really get a good introduction to complex numbers. So if you've heard about the fundamental theorem of algebra, great. If you haven't, don't worry about it. Just know that there is one. So there's a fundamental theorem of algebra, it's fundamental theorem of calculus, and now there's this fundamental theorem of line integrals. So this is a big result. I'm going to refer to this as FTLI. FTLI. If you ever see that FTLI somewhere, I'm talking about the fundamental theorem of line integrals. So what does it say? The fundamental theorem of line integrals says that if C is a smooth curve, now smooth was there was a definition for smooth. Okay, so if it's smooth and it's given by some vector function R of t, and we're given some restriction on t, and if f is a differentiable function, so that means f is some, so let's not confuse things. C is a curve, right? So we're given some curve through space, and we're given f, which is a scalar function, not a vector field, a scalar function. It's differentiable. It could have 2 or 3 variables, doesn't matter, such that the gradient of f is continuous on C. Then the line integral on the curve C of the gradient vector field of f dotted with dr will be equal to f evaluated at RB minus f evaluated at R of A. Okay, what the hell is this saying? Okay, this is saying that this theorem says that the line integral of a conservative vector field is simply the difference of the value of the function f at the endpoints. I'll explain that a little more later. Further, the line integral on any 2 paths that connect the same 2 points are equal if f is a conservative vector field. Okay, there's a lot to wrap our heads around with this, all right? It's a really nice theorem, but you have to understand what's going on. So remember this. Let's do a 2-dimensional idea first. If I give you a scalar function, f of x, y, equals, let's just say x squared plus y. Okay, we know that in 2-dimensional space, in 3-dimensional space, this would graph like this paraboloid looking thing, right? Like this. Okay, we were told that the gradient of this is just a vector that is created by taking the partials of each of those. So if I take the gradient of this, I'll just get 2x, 2y, and that's my gradient vector field. What this represents is in 2-dimensional space, some vector field. Right now, in this case, it's going to look probably like this. It's going to go away from the center like this. Actually, yeah, like that, going away from the center. What that vector field, this is a vector field, right? This vector field represents, if you were to go to like some point, let's say in the XY, I'll do it over here, some point in the XY plane, which would correspond to some point here in the XY plane on the left. If you were to go up to that surface, to where you are on that surface, that vector there would tell you the direction of steepest ascent, right? Go with me? Okay, so the fundamental theorem of line integrals says this. This is the mind-blowing thing. If you take a curve over here, okay, so separate these 2 ideas. If I give you a vector field, okay, I give you some vector field, and I ask you to move through this vector field in a path, R of t, okay? If this vector field that we're talking about, if it's actually just the gradient of some scalar function, if that vector field is just the gradient of some scalar function here, then if you want to know the work that you do here, all you have to do is take this, let's call this the starting, let's call this A, and let's call this B. All you have to do is take this point over here in this space. Let's just draw that curve over here. What you do is you take that point and you plug it into the surface, and it's going to spit out a number. That'll tell you how high you are over here, some number. And you subtract from that, plugging in the A here, and that'll give you some height over here. It's a number. You take those two numbers and subtract them, and that gives you the work over here. It's pretty mind-blowing, but it kind of makes sense if you think about it in the sense of what Cal 2 told you, right? Cal 2 told you that if you have a function, right, over here, f, and you started at A and ended at B, and you wanted to know the area, let me do this backwards. Yeah, I'll do it this way. Yeah, then, and that's not working, hold on. I'm trying to make it look exactly like this. Yeah, okay, so if you have some function here, f, and you wanted to know the area under here, which we know is an integral, right? It's the integral of what? Integral from a to b of this, f of x dx, turns out to be the antiderivative, capital F, of b minus capital F of a, which means that if you can graph me the antiderivative over here, right? Here's a little f, the antiderivative is over here. All you have to do is go to the endpoint b, plug it in. That'll give you that number, okay? That's that number. And then go to a, plug that into the antiderivative, take that number and plug it in here, subtract the two, and you got the area underneath. That's pretty much what we're doing here. We're saying if you want to know the work, which is adding up the work along this whole thing, then if this is the gradient of something, if this is the derivative, just like this right here, little f is the derivative of big F, then as long as you can go back to this and evaluate the two endpoints, you're going to be able to compute the work. Okay. I know that's a lot to understand and swallow. I hope that that kind of makes sense. But what the second part of this, and I'll bring the note back up, the second part says, because of this, if you do a different path, like let's say I do a different path that does some crazy shit like this and ends here at B, the work along the green path and the work along the red path will be equal, because the fundamental theorem of calculus says that as long as this is a gradient vector field, then when we go backwards here, all we're still going to be doing is evaluating at these two endpoints. We don't care about the path. It's just all about the two endpoints. So if we start and end at the same place, we're gonna get the same answer regardless of what path, right? I do some other path does this, as long as I start and end at the same point, I'm good. The key is that the field has to be a gradient vector field, which means that it must be conservative, because that's what the definition of a conservative vector field is. It is the gradient of some scalar function. Okay, I know that's a lot to take in.
So we're pretty much just working with vectors, subtracting vectors.
We are going to be subtracting a function evaluated along a vector path at the endpoints. Let's do an example. I think, you know, when I do one, I'm hoping it'll kind of start to come to light a little bit.
Just wondering, does that mean that there's some that aren't conserved?
Yeah, so conservative vector fields are very nice vector fields. They're nice to work with because we can use the fundamental theorem of calculus. If the vector field is not conservative, then you can't use this, and that means you have to grind out the work. The good news is that most vector fields that we work with in real life are conservative, and so this is a nice result. All right, here we go. Oh, hey, check that out. That look familiar? Let little f of x, y be equal to x squared plus y squared, and c is this curve, t sine t, t cosine t. You know what? Hold on, let me back something up. I'm trying to see. Where was the first problem we did with vector fields where we wanted work here? Okay, we did this last class, didn't we? Find the work done by the gradient vector field, blah, 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 traversing the top quarter of the unit circle. Did we finish it? I don't think we did. Did we? Go back and look at my notes. Did we actually get an answer? Oh, we never finished it out, did we? We never finished out. Okay, I'm not going to go back to it then. Let's just move on. Let's do this example if I can find it. What is it? Okay, here it is. We're going to do this example here. All right, let little f be this, and we want to find the work done by the gradient vector field. So do y'all understand that this right here is the vector field we're supposed to be doing this with? dr, integral over c, right? Yes? So because that's the gradient of little f, can we use the fundamental theorem of line integrals? Since our field is the gradient of little f, can we use the fundamental line?
Yes.
Fundamental theorem? Yes, we can, right? Because it says in the theorem, wrong one. It says that as long as your vector field is the gradient of some scalar function, then this just becomes this. That's all it becomes. So I'm going to use that. I'm going to say, okay, well, then that just becomes f evaluated at r of b minus f evaluated at r of a. Now, what is r of b and r of a? What are those physically?
We would take our boundaries and plug them into the, what's it called? R of t.
Yeah, so do y'all agree that this is the endpoint? This is the endpoint of the R curve? And this is the starting point of the R curve. That's what this is and this is, right? So the endpoint of this curve is what happens at pi. So let's figure that out over here. R of b really means r of pi. And r of pi is, let's see, if we plug pi in here, what's sine of pi? 0. So we get 0 here, get the vector 0, and then when we plug in pi here, we should just get negative pi. Right? Pi here is pi, and then cosine of pi is -1, so we get negative pi there. R of a is r of 0. And that should give us the vector 0, 0, right in here. So that means what we need to do is evaluate the scalar function at the vector point negative, sorry, I did those, yeah, that's right, negative pi. Then the scalar function evaluated at 0, 0. Now this is weird notation, and I even state that in the notes. I say, hey, look, don't freak out about the notation. I say it in a little while. No, I guess I don't. Don't freak out about this notation. Taking a scalar function, evaluating it, this vector looks weird, but just look at this as like, this is the x coordinate and the y coordinate now. And we're going to be plugging that into little f, which is this guy right here. Okay, just plug it in. And what do we get? So if you plug in 0 for x, you get 0 squared plus negative pi for y, so negative pi squared. Then you subtract from that 0 being plugged into that. So 0 squared plus 0 squared. And your answer is pi squared. Bam, we're done. Now, let me just show you. If you didn't use the fundamental theorem of line integrals, here's what you would have had to have done. You would have had to have found this gradient vector field. So you would have had to say, okay, my vector field is going to be the partial, so 2x, 2y. You would have also had to have found the derivative of this. So you would have that r prime, let me just show this separate here. You would have had r prime of t equals the derivative, shit, some product rules in here. So sine t plus t cosine t, and then the other one would be cosine t minus t sine t. That's your derivative. And now what you'd have to do is do the integral from 0 to pi. You would have to take this field, evaluate it at x and y along this curve. So replace x with t sine t and y with t cosine t. So it'd become 2t sine t, 2t cosine t. You would have to dot that with this guy. Oh man. dt. And then you go dot, and then you go integrate. Can I stop? That's like going to take, there's going to be like integration by parts in there. There's going to be lots of messy things. Let me do one more thing. Hold on. I'm going to multiply it, okay? I'll just multiply it at least. This will be 2t sine squared t minus, let's see, this times this, 2t squared sine t cosine t. Okay, that's that times that. And then when I do this times this, I'm going to get plus 2t cosine squared t minus 2t squared cosine t sine t. Wait a minute, maybe this isn't going to be that bad.
Switch the sign. Not bad. The first
Right.
should be sine t plus t cosine t.
Yeah. You got your little wind tunnel going, so it's a little hard to hear you.
Sorry.
That's all right. I know you don't hear it, so. Okay,
Sine.
yeah,
I was saying you switched to sign.
I switched to sine.
Yeah, it should be sine t plus t cosine t. Up one.
Oh, right there should be a plus.
Yeah.
Oh, yeah, that is a plus. Okay, that might actually make things nice, right? Because I'll have this and this will be plus. And then these two cancel.
And then you'll get rid of the sine squared and cosine squared and just have 2t.
Yeah, these two put together, you can factor out a 2t and you'll be left with sine squared plus cosine squared. That's a 1. So you get 2t dt, which is just going to be t squared evaluated from 0 to pi, which is just going to give you pi squared. Same answer. Not a coincidence. A lot more work, right? A lot more work. The reason I know that I could use the fundamental theorem of line integrals was because I was told to do the line integral over C of the gradient vector field. All right, that's why I know I could use it. Let's look at the next problem now. Oh, well, maybe not. Hold on, got a couple more things to get through here. Okay, so we did that. All right, path independence. This is a theorem. So when you have a curve that starts at A and ends at B, if A and B are the same, then it's a closed curve. Make sense, right? You start at the same point that you end. You'll have a closed curve. A closed path is a path with the same initial and terminal points. Check this out. If you're doing the line integral over C of FDR, so this is basically work, we will call that path, we will say that it is path independent if and only if the line integral over that vector field is 0 for every closed path. So we're defining something here. We're calling something path independent. So to be path independent means that if you take the vector field and you move along any closed path, I'll draw you a picture. So let's say I have a field here, and the field means there's vectors everywhere, all right? and you give me a path that starts somewhere and ends somewhere, same point. If I calculate the work and I get 0, and I do that for every closed curve in there, so I do another closed curve somewhere else. And then another closed curve somewhere else. And then another closed curve somewhere else. If I keep getting 0 over and over and over and over for every curve that you ever put here, then we will say that this is path independent. But that's a very hard thing to do. I mean, that's a hard theorem to use because it requires that we actually test every single path here, right? Which is impossible for us to do. You can't test every path. However, if the vector field is conservative, right? If it's a conservative vector field, then we know that the line integral on that vector field is always just the difference of the two endpoints of the curve itself. And if all of the curves are closed, then where I start and end is always the same point, which means that I'm always going to get 0. But that only works if the vector field was conservative, or if it was the gradient of some scalar function. And that leads to this final thing. So line integrals on closed paths of conservative vector fields are path independent. They always give you an answer of 0. We'll see this in use later. All right, so the big question should be now, look, if I give you a little f, right? If I give you a little f, a scalar function, you can always calculate the gradient vector field. You can just do the partials. That's easy. And you know then that you can use fundamental theorem of line integrals for those, for that vector field that you've created. But what if I just give you an arbitrary vector field? Say, here you go. You can't actually use the fundamental theorem of line integrals unless you know it's conservative, right? You have to know it's conservative. You have to know it's the gradient of something. And so we have a nice theorem here that helps us determine whether or not a vector field is conservative or not. And there is a very simple way to check. So let's say you're given a vector field. Let's say that vector field is defined on a simply connected region in D. So this is just something I have to put in here because it's part of the theorem. A region in two-dimensional space is called simply connected if there's no like holes in it like this. So as long as we're talking about a region that's simply connected, then you can run this test. So here's what you need to have a conservative vector field. You need that if you look at the vector field as being a p function and a q function. So the x component is p, the y component is q. If you take the partial of p with respect to y, it better be equal to the partial of q with respect to x. If that's true, you're talking about a conservative vector field. So let's do an example. Is this vector field conservative? All right, so is it conservative? So the way I do this is I say, okay, it's a two-dimensional vector field. This part is my p function. This part is my q function. And now I'm just going to run this test. So I'm going to take the partial of p with respect to y. That will just be 2x. Then I take the partial of q with respect to x, and what is it? 2x, right? Those are the same. Check. That's a conservative vector field. So that means that if I were to be asked to find the line integral along that vector field, right? If I were being asked to find the work along that vector field, here's what I can tell you. I can tell you that if the curve is closed, which means it starts and ends at the same point, the answer is going to be what? 0, right? If it's a closed curve. Now, if it's not a closed curve, then I can use the fundamental theorem of line integrals because it's conservative. The problem with that is that I would need to know what little f was. Does that make sense? Because to use the fundamental theorem of line integrals, you have to know what little f is. Okay, I don't want to get too far ahead of ourselves here. Right now, all that's important is if you are given a vector function, can you find, determine whether or not it's conservative or not? Simple check to do it. All right, now how to create what we call the potential function. So I said before when we first defined what a conservative vector field was, I said that it's conservative if there exists a scalar function such that the gradient of the little f is equal to f. In such a case, little f is called the potential function for big F, or for the field. We now learn how to find potential functions, and we're going to use what's called partial integration. So here, this is a good example. We'll go to this here. Here we go. First question, is it conservative? Check for yourself. What do you need to check? Is partial of p with respect to y equal to the partial of q with respect to x? That's the question, right? This is p. P is this guy right here. And q is this one. Check that for yourself real quick. I'm gonna just go get my drink real quick. All right, is it conservative?
Yes.
Okay, it is. Partial p with respect to y is just 2x. And that's the partial q with respect. So easy check, right? This is correct. Now, find the potential function. So you really need to make sure you understand what we're asking for here. We need to find the little f such that when we take the gradient of that little f, we get capital F. That means that the gradient of f, which by definition is a vector, partial of f with respect to x and partial of f with respect to y, that must equal the field we're talking about here, 1 plus 2xy plus natural log x, comma x squared. Any questions on this equation right here that I set up? In order to say that this is conservative, it means that there's some little f that when I take its gradient, I get this, I get that. That means the gradient has to be equal to that. And now what I'm going to do is the process of what's called partial integration. So I'm going to start with the first equation I know must be true. Those two have to be equal. So I'm going to put here the partial of f with respect to x must be equal to 1 plus 2xy plus natural log of x. Remember, we are trying to get back to little f, right? We really want to find what little f is. And here's what I can tell you, that the partial of little f with respect to x is this. That means, though, that if I integrate little f with respect to x dx and integrate the other side with respect to x, that should get me back to little f, right? It's like we're taking the antiderivative with respect to x of the derivative with respect to x. So the left side should just spit out little f, right? Now the right side, I'm taking the antiderivative with respect to x, we should get what?
xy squared.
Plus x squared y, right? Is that what I'm saying? Yeah, x squared y. Plus now the antiderivative of natural log of x, some people know it, some people know they've seen it. Some people haven't memorized, some people don't. No.
I have it written down in my Cal 2 book somewhere.
It's x ln x minus x. That's the antiderivative of the natural log of x. As Cal 3 students moving on to like differential equations or something like that, that's probably something you should try and get memorized. Everyone knows the derivative of natural log of x is 1 over x, but we're talking about the antiderivative. So it comes up enough that you should just try and learn it by now. Okay, what are we missing? We integrated.
Some constant of integration in respects to y.
Yeah, so this, and remember Daniel, when we talked about this a few weeks ago?
Yeah, I do actually.
Yeah, so what we would normally say in a Cal 2 class is we would say plus a constant. But the thing is, it could be more than that. It could have some y's in it. Because when we take the partial of this with respect to x, we got to get back this. So if this, if this had, of course, like a 4 out here, and we took the derivative, we would get that with respect to x. But if this had, let's say, a y cubed, we would still get back this if we took the derivative with respect to x. Or we could have, something like sine of y here, and we'd take derivative, we'd still get this. So this is now going to be more than just a constant. It's going to be some function of y that I don't even know. So I'm put h of y. Just some function of y. I don't know what it is. Okay. So what we have so far is we have little f. This is what little f is. Oh, you know what? Those x's cancel. Okay. We have a little f, but we're off by a function of y at the most. Now I'm going to use the other equation, but watch how I do it. I'm going to take this equation now, and I'm going to take the partial of it with respect to y. So if I take the partial of this with respect to y, I get x squared. Derivative of all of this is 0 because there are no y's in here, right? And then what's the derivative of this with respect to y? I don't know, right? It's just the derivative of h with respect to y. I'm going to write it that way. It's just the derivative of h with respect to y. I could have written this, h prime y. I could have done that also, but I'm going to write h with respect to y like this. But this must match this, right? Don't they have to match? So if these have to match, then that would imply that x squared plus the derivative of h with respect to y must equal x squared, which means that the derivative of h with respect to y must be equal to 0 if I just subtract x squared on both sides. So I want to know what this is, though. I want to know what h of y is. I don't want to know what the derivative of h with respect to y is. I know that's 0, but I need this. So what would h be? Or how could we get h, I should say?
We would integrate 0 and then we would just have some constant of integration left over.
Yeah, now we're going to integrate both sides of this with respect to y. And that will tell me the left side is just h. If you like, you can write h of y equals the antiderivative of 0 is a constant. So that means that little f, this is my final answer, should be x squared y plus x natural log x plus any constant I want. That is the potential function for this vector field. So let's see if you can put this together. Here we go. If f is equal to the vector field 1 plus 2xy plus natural of x comma x squared, find the work done, right? This is work, the work integral, where c is given by this path. Put a star here. This is 2 stars, 3 stars. So part of your brain wants to do this. Part of your brain wants to say, oh, I'm going to go and use this formula here, where I'm going to have to find the vector function, take its derivative, evaluate the field on that. You know, part of you wants to maybe do that, right? Because you have the curve, we can take the derivative of that. We have the vector field, we can go ahead and plug this in for x and y, and then we could dot that and do the integration, right? We could do that. But what's better?
The fundamental theorem of line integrals.
Yeah, so why can we use a fundamental theorem of line integrals?
Well, we just found that was a conservative vector field.
Yeah, we just did this problem, right? I gave you this vector field. That's the exact vector field we just did. We showed it was conservative and we found its potential function, right? Here was the potential function right here for that vector field. So we know right now that this is our scalar function. This is the potential function. So by the fundamental theorem of line integrals, we know that this is equal to line integral over the gradient of little f dot dr, because we know that this f came from the gradient of that. But by the fundamental theorem of line integrals, that says we just need to evaluate f at the endpoint of the curve and subtract from that f evaluated at that first starting point of the curve. So can somebody tell me just in layman's terms, like what we need to do to answer this question?
We need to evaluate R at the endpoints and then plug in those vectors as if they were a point into our F, and then bada bing, bada boom, we're done.
Yes. Yes, you have to have the bada bing and the bada boom. It's got to be part of the work, though. I like that, Daniel. All right, so Daniel said that right. I'm going to say it a slightly different way. What I'm going to do is I'm going to plug 2 into this. And that's going to give me a vector that I'm going to plug in here. Then I'm going to plug 1 into this, and that's going to give me the vector that goes in here. And I'm going to take both of those, plug both of those vectors into this scalar function, which is a little weird, but it's just basically replace x and y with the x and y components of the vector. And I'll subtract the 2. Okay, so let's do it. R of b. That means R of 2. And that means I'm going to get a vector. If I plug 2 in here for t, I get 5, 4. And then you plug in 1, 1, yeah, 1, and you get 2, 3. Now I'm ready for the calculation. This is going to be f evaluated at 5, 4 minus f evaluated at 2, 3. And that means we're going to plug 5, 4 into this. and subtract 5, 4 into that. Subtract 2, 3 into that. So 5 for x, so I'm getting 5 squared times 4 plus 5 times natural log 5. Now, plus c, I don't need plus c because I can choose any c I want, so I'm going to choose 0. Right? Understand? I can use any c. So I'm going to just choose 0 to be c because it would cancel out on this side anyway. All right? It would cancel when you subtract. So now I plug in 2, so we've got 2 squared times 3 plus 3 ln 3. And there you go, 25 4. It's 100 plus 5 ln 5 minus 4, 3, 12 plus 3 ln 3. So that's gonna be 88 plus natural log of
At 2 ln 2.
what's that? Did I do? Oh, is x? Yeah, 2 ln 2. Thank you. 2 ln 2. So that's natural log of 5 to the 5 plus natural log of 2 to the 2. I can do that, right? Powers can come, or numbers can come up as powers on logs. And I can even put those two logs together into one log, where it'd be 5 to the 5th times 2 to the 2nd. And then figure out whatever that is. Can you appreciate how much easier that is than actually having to do the grind it out? So the last thing I want you to do is like, I give you a mini exam and I give you a problem, right? And I ask you to do this right here. And then you become very robotic and you're like, oh, I'm going to go and find the derivative of this. And then I'm going to dot these two. If you may go down that road and not be able to ever get to an answer because it just may be way too complicated. If you find yourself in that situation, figure out if it's conservative. Like figure out, is it a conservative vector field? If it is, go figure out its potential function. Then you can use fundamental line integrals, fundamental theorem of line integrals, and you never have to do any integration, really. I mean, you do to get the potential function, but you don't have to do any of the integration in here. So it's a very nice result. All right, this is probably, yeah, this is going to be the last example here. Okay, I have very conveniently avoided vector fields that are 3-dimensional. I have only done vector fields that are 2-dimensional. And we have seen that to check to see if a 2-dimensional vector field is conservative, we have an easy way of checking. Okay, there's an easy check to see if a 2-dimensional vector field is conservative. But if it's a 3-dimensional vector field, we do not have a way of checking to see if it's conservative yet. We will, not yet, okay? But if I give you a vector field, you can still try and find a potential function. Without knowing if it even exists, you can still try. So if I give you this vector field and say, find the potential function, then you would say, all right, well, I need to find little f such that the gradient of little f, which is equal to the partial of f with respect to x, partial of f with respect to y. Now we have a partial of f with respect to z because it's 3 components, or 3 variables. That must equal this, 2xz plus y squared 2xy x squared plus 3z squared. So we need to find a little f such that when I take its gradient, I get a gradient vector that matches this field. And I'm going to start the way I started last time. I'm going to set those two equal to one another. So the partial of f with respect to x must be equal to 2xz plus y squared. Any questions on what I'm doing or the path I'm going down here? To get little f, what do I do?
partial integration.
Integrate. So I'm integrating with respect to what here?
X.
X. Do that on both sides. Okay, now on the left side, we get little f, which is great. On the right side, we integrate with respect to x, we get x squared z plus xy squared plus, and now the drum roll.
Let me.
Okay, go ahead, Daniel.
A function of integration in respects to y and z.
Both, right?
Yes.
So we could have a constant here. We could have something with just y in it. We could have something with just z in it, or we could have something with both y and z in it. Just can't have x in it. So I'm going to put here h, some function of y and z, like a surface almost, right? Function of two variables. Okay, so far we know little f, but we're off by an entire function of two variables, perhaps. All right, now what we do is we say, all right, we're going to kind of use this information against itself. So I'm going to take this and take the derivative now with respect to y, the partial. And now take the derivative with respect to y everywhere, and you'll get, okay, this is 0 because there's no y's here. Here we get 2xy, plus, now this derivative with respect to y would be h with respect to y. But that has to be equal to that, doesn't it? These have to match, like this partial of f with respect to y did not come from here. It came from this information. So once we had this, we said, okay, well, this must match up with this, right? Because that's what the second component must be. And that again implies, just like the previous problem, that the partial of h with respect to y must be 0. Subtract 2xy on both sides. Now I want to get what h is. So I integrate this with respect to y, integrate 0 with respect to y. The left side is h, and the right side, drum roll.
Any constant.
Any constant? What else could it be?
I guess any constant and z.
It could have a z in there also. See, because remember, h was originally, we are thinking in our minds, h could be y, could have y's and z's in it, right? And so when we differentiated this, we said, okay, so the derivative with respect to y of h with respect to y is going to be here. I don't know what it is yet. And then we set these equal and we said, oh, okay, well, that means the derivative with respect to y has to be 0. We integrate that with respect to y, and now I can say what h is. H is, well, all I know is that the derivative with respect to y was 0, right? I don't know what the derivative with respect to z is. So this could potentially be some function, I'm gonna call it g, of z. So now here's what I can tell you about f. F is equal to x squared z plus xy squared plus the h function, which before I thought could have y's and z's in it. But now I've deduced that it can only have z's in it. So it's some function of z here. And then I play the game again. I take the partial of this with respect to z now. If we do that, we get x squared, 0, and then whatever the derivative of this is with respect to z, which I don't know yet. But that must match whatever's up here. right? It's got to match this last piece. So it must be x squared plus 3z squared. The x squareds cancel, and you get g, partial g with respect to z is equal to 3z squared. And now you can integrate both sides of this with respect to z. We're almost done. And you get that g must then be z cubed plus some constant. So finally, what I can tell you is that this must be equal to x squared z plus xy squared plus my g function, which I just said was z cubed plus c. And there it is. That's the potential function. There's some good news here. The good news is that you can check your answer, right? You can just check your answer. Take the gradient of this. So take the partial with respect to x, you get 2x, you get 2xz, boom. Partial with respect to x, you get plus y squared, that's this. Okay, done with that. Partial of this with respect to y, all you get is 2xy, that's this. And then you do the partial with respect to z, and you get, let's see, x squared, and then that's nothing, and then plus 3z squared, there it is. So we can check our answer. So this particular vector function, this one that we were looking at, we were able to find a potential function. Do you think that every vector field has a potential function?
No,
No, because that would mean every vector field is conservative. And if every vector field was conservative, then we wouldn't even call them conservative because there would be no distinction between any other thing. So not every vector field would be conservative. I'm curious to know what would happen if you had a non-conservative vector field and you go try and find its potential function. You would run into an obvious problem if you tried it. You would just start working out the partial integration like this, and things wouldn't work out. Like, let me show you an example. Like, not an example, but let me just say we go through this. Let's say we say, okay, the partial of f of x has to be equal to this. We start with that. Then we integrate and we say, okay, this right here, this is what f is. We're off by a function of y and z. And then we take the derivative here. And let's say at this point right here, when we take the derivative and we try and match it up to this, let's say when we matched it, this piece in here wasn't that. What if it was instead something like 3x squared y, like that? So instead of that, it was this. Then there's just no way you can make those equal to one another. So it would be obvious that there's no way you can match it up. So, okay, that is going to conclude this section, I believe. Let me just make sure on the notes. Yeah, that's it. All right, we have 2 minutes. Wanted to look real quick at the mini exam and what we have for that. We had one of them was due today, right? Was a mini exam due today? Where the heck did it go? Oh, did I open it here? No. There it is. I'm just trying to see what you can do and what you can't do. So this one's due in a week. And the first question is, here's a vector field. And I'm telling you that vector field is conservative. And I tell you to find its potential function. Okay, so you have to just go find the potential function for that vector field. Then once you do that, find the work done over that vector field where here's the curve that I give you. So I need to zoom out a little bit. I give you this curve and I draw its picture right here. Okay, this is the picture of that curve. And I show you the direction of the curve. So it starts here and it goes and it comes like this and it ends right there. You can do number one. In theory, you should be able to do number one now. Number two, we're not ready for. Because we haven't talked about the line integral with the little circle around it like that. We haven't talked about what that is yet. And I highly recommend that you do not try and do this problem yet. Okay, because we don't have what we need. And so you can make this problem really hard, or you can make it really easy. And I want you to do it the easy way. So, and then this last one, again, you can't do that yet because it asks for you to figure out where that vector field is both simultaneously irrotational and incompressible. We haven't even talked about that yet. So as of right now, mini exam 6 consists of one problem that you can do. I think by the end of next class, we'll be able to do number 2, but we may not get to number 3. We'll just see.
Hey, I'll take a 33.
Yeah, no, I would only grade it off of what you can do. I might just push the deadline, that's all. I might push the deadline to the Monday, the following, Monday, right? Today's Wednesday, yeah. So yeah, that's what I would do. I'd probably just push it out to the 3rd. But isn't that our last week of classes?
Yeah, it is.
It is. That's our last week of classes. So I'm kind of running out of time to collect mini exams. We're just running out of time, period. I'm trying to go as fast as I can, but I mean, we're just finishing up fundamental theorem of line integrals. We have Green's theorem and divergence. We should be able to get that in one day, hopefully. So that's next Monday. And then this is just, God damn.
Yeah,
I might have to give you like a take-home assignment for you to go watch some videos before class or something, because there's just so much there still. Wish we had an extra week, but that's what it is. Okay, everyone. Call it.